Hello students, welcome back. In the previous lesson, we went through really important theorem that is, given linear map in finite dimensional vector spaces, we can associate a matrix associated to this. If this is big if, we have set bases v1 through vn and w1 through wm. If we have different bases, then we'll have different matrices. Okay, so that's what we did. And let's consider composition and inverse, because we went through matrix multiplication, and if we do another matrix multiplication, what is it? And also we talked about matrix inversion, inverse matrices. Well, how is it related to the map? Well, the result is pretty straightforward as a matter of fact. If we have composite map G composition F, then the matrix associated to this composite map is matrix multiplication B times A. So A is associated to F and B is associated to G. Then composite map G composition F is associated to B times A. Let's see, maybe some color coding would help. Red, blue, red, blue, and this blue, and that's red. See, U to V and V to W, and if you take composite map, then U to W directly. So U to V first, and then V to W. Composite map, U to W directly. And matrix associated to this is A and B respectively. And then multiplication is to the right, you see. Okay, never mind about the proof. So if you have matrix, column vector is to the right, and then applies A first, because we're doing F first, and then next is G. So from the right, information flows to the left from X, and then apply A, and then apply B. This is associated to G composition F of G. So right hand side here, we have arbitrary vector V. Coming from U, so let me use small u here. So arbitrary vector U from vector space U, and then map F is applied, and then map G is applied. So U is going to V, and then V is going to W. So information flow is from right to left. Again, from right to left. Same order, same matrix multiplication. How about the inverse? Same idea. Inverse map is associated to inverse matrix. That's basically it. Now, do we have enough time to prove these? Okay, let's go ahead. It's relatively less important, but let's do it anyway. Okay, here's a basic scheme. G composition F is sending U to V and V to W. And then in terms of the coordinate expressions, X is going to Y and Y to Z, and X, Y, and Z are column vectors. Coordinates of these vectors U, V, and W with respect to this basis, the second basis, and the third basis respectively. So Y equal to AX and then Z equal to BY, put those together, then Z equals to, let's see, BY, which is b of ax because y is equal to ax. And that's about it. How about the inverse? We just do matrix multiplication to come back to the original. X is going to y and y is coming back to x. V is going to w, w is coming back to v, and the column vectors are coordinate expressions of v and w respectively. So x is going to y, y is coming back to x. So y is equal to ax, and then x is by. So what do you get? X is coming back to b times y, which is b times ax because y is equal to bx, y equals to ax, yeah? And end result is therefore x is equal to ba, and what do you get? That's the identity. So b has to be A inverse. So the matrix associated to F inverse, which I named originally tentatively as B, turned out to be the same as A inverse, just as expected. And that's the proof. And I don't know whether I'll ever write this kind of proof because, overly theoretical. But end result, everybody should know. Composition, just matrix multiplication. Inverse, matrix inversion. Let's see, do we have an example here? Let's see. Example here. Okay, so rotation map. And then taking the composite map, okay. Composition, rotation by angle alpha, and then rotation by angle beta later on. So it's a matrix multiplication. Alpha first, and then beta later, right? And rotation by alpha and then beta, that's the same as rotation by alpha plus beta directly. So if you compare this and then that, you get rotation by alpha plus beta versus alpha first, beta later. And it follows that we have, well, removing this arbitrary xy's, we have this matrix computation. And do some brute force computation, and what you get? We just end up with the sum identity of sine and cosine. Cosine of alpha plus beta is this one, okay. And then sine of alpha plus beta is this one except for the negative sign. And the sine of alpha plus beta is this one. And then cosine of alpha plus beta is that one. And we end up with the sum identity for sine and cosine. It's a little bit better proof than the one we discussed earlier in the previous video, which was kind of inherited from 1600. You see, this is visualization. In this case, negative 0.43, so a little bit less than half pi, a little bit less than 90 degrees, but clockwise. And then composite map, let's see. Is there a good visualization here? Yeah, I guess so. 1, 0 is going to xy, alright, and then xy to capital XY versus 1, 0 all the way to capital XY. Yeah, those are the same. You see, rotation of alpha plus beta directly is alpha first, beta later, and that's a visualization of this computation. Alpha first, beta later versus alpha plus beta directly. And the right hand side is, of course, matrix multiplication. Okay, all right. We went through example, and at the same time, we ended up proving the sum identity of sine and cosine. That's where I'm going to stop. Thank you.